Thank you very much, and I'm really grateful for inviting me here. This is not actually going to be a mini course. It's a series of two independent lectures, and the only common theme in these lectures is that the problem comes from one area of mathematics and the solution comes from a completely different area. And the first part of it is a joint work with Alexander Barvinok from University of Michigan, and we are going to talk about solvability of quadratic equations. So let's assume that we have several polynomials of degree 2, and these polynomials are of n real variables, and we want to ask a question whether there exists an x real such that qj of x is 0 for j in M. First, this is a classical problem in algebraic geometry, and if you have any polynomial over the complex field and you are looking for a complex solution, or in general the solution over the algebraically closed field, the problem is beaten to death in algebraic geometry. However, if you take a real field and the polynomials are real, more or less nothing is known except for the linear case. We kind of know how to solve a linear system. And quadratic system is the next step of generality, but this is not the main reason. The main reason is that any polynomial system of reals can be reduced to the quadratic ones, which is very easy. For example, if you have a monomial x1 cubed x2, then you introduce a new variable y1, which is x1 squared, y2, which is x1, x2, and this becomes a second degree monomial, y1, y2. So you can replace any polynomial equation with a number of quadratic equations by adding some new variables. And so if you can solve the problem of solvability of quadratic systems, you can determine solvability of any polynomial system. This is, of course, too much to demand, and nobody believes that a checkable condition, necessary and sufficient condition for the solvability of a polynomial system can be written, at least not checkable in polynomial times. So we settle for something less. We will settle for a sufficient condition. And then, before we write this sufficient condition, let me simplify the system as much as I can. A nice thing about this problem is that I don't have to talk about its history because it's non-existent. Okay. So let's first we can get rid of the linear terms. So qj of x is going to be a jx inner product with x plus bj product with x plus c. J And AJ is a symmetric matrix, not necessarily positive definite, of course. And first we can easily get rid of the linear term. We just introduce a new variable, say tau. And instead of the polynomial qj of x, we write a polynomial qj of tau inverse x times tau squared. In this case, the first term remains intact. The second term gets a coefficient tau. And becomes quadratic, and the third term gets a coefficient tau squared. And then we add an equation, tau squared equals 1. And we are down to the polynomial, which is a homogeneous polynomial of degree 2 and a constant part. So our system will look like qj, aj x times x equals alpha j. And there is another simplification which is much less trivial than that. You can actually choose a specific value for alpha j, and we're going to choose, without loss of generality, we can assume that alpha j is the trace of aj. I'll save time to describe how to find this change of variables, but we can do it. And so we have this specific system, and let's look at it. If I have a bunch of such equations, then any linear combination of these equations will be also an equation of this type because the trace is linear. And this means that I can, instead of the original matrices AJ, I can use the matrices which are the simplest I can obtain using linear combinations. So what are these simplest matrices? Well, there is a canonical inner product on the space of square matrices. A times B is the trace of A transpose B. In particular, if you take a norm with respect to this inner product, this is going to be the square root of the squares of the entries. This is so-called Hilbert-Schmidt or Frobenius norm. So this is just it just vectorizes the matrix A and evaluates the Euclidean norm of it. So if I have a Euclidean structure on the space of matrices, then the simplest possible collection of matrices in this linear space will be an orthonormal system. So without loss of generality, we will assume that AJ form an orthonormal system, and we want to solve this system of equations. Now I can formulate the statement. So let A1, etc., AM be an orthonormal system of n by n symmetric matrices if some condition holds, then the system A jx times x equals trace of A j has a solution. Now, what is the condition? Let me form a combination of these AJs. I take the sum j from 1 to m, from 1 to m of aj squared. Then I take the operator norm of it. And if this quantity is bounded by some absolute constant eta over m, then the solution exists. And eta here is an absolute constant. If you analyze the proof, then say 10 to the negative 4 would do. Okay. First of all, let's look at this condition. I assume that the matrices form an orthonormal system, which means that the Hilbert-Schmidt norm of each matrix is 1, and if the matrix is, say, generic, if it has a large stable rank, then its norm is going to be small. And if its norm is small, the norm of the square is even smaller. So there is nothing surprising in the fact that this quantity may be small, despite that the matrices themselves are normalized. Second, if you follow the process, at a certain point, we will have to orthogonalize the system of matrices. This can be done in many different ways. So we arrive to different collections of these matrices AJ. And regardless of the way we orthogonalize them, this quantity, the norm of this sum, remains the same, so which points out that this may be a right quantity to deal with. And another remark is that the whole process is efficiently computable. So you have to orthogonalize the system of matrices for which you have Gram-Schmidt, which is efficient, and then you have to evaluate the norm of this matrix. AJs are symmetric, AJ squared are positive semi-definite, so the norm is actually the largest eigenvalue of this matrix, and evaluating the largest eigenvalue or estimating the largest eigenvalue is efficient. Okay. Any questions about the formulation? Now, how would one prove it, and how would one, being an analyst, approach a problem in algebraic geometry? What we know is to prove inequalities, and we want to introduce a gap and show that if the system has a solution, then a certain parameter is below some value, and If not, it's above some value. And this means that the problem should be robust. And again, here in the setup, nothing is random. We are looking at the deterministic system, and we want to determine whether a real solution exists. And here we have a problem. This gap is basically non-existent. Let's consider a couple of examples. So let's consider a system, say, yj minus yk, the Euclidean norm, squared equals 1 for jk in, let's say, n, and j is different from k. Everybody knows what this system describes. All the distances are the same. This is a simplex. And a simplex can exist only if y, the lowest dimension when the simplex with n vertices can exist is yj should be in n minus 1 dimensional space. Now let's introduce a relaxation of this problem. Let's take epsilon positive, and this time yj minus yk is between 1 plus epsilon and 1 minus epsilon. In this case, we have Johnson-Lindenstrauss lemma, which shows that such yj's exist in the space R, say L, where L is about log n. So relaxing the right-hand sides a little bit drops us in the dimension in a very significant way. But maybe taking epsilon extremely small, we will exclude this example. But this is not the case. We can consider an even simpler example. Let's consider a 2-by-2 system. x1, x2 equals 1, x1 squared equals 0. Of course, there are no solutions. But for any positive delta, you can have an almost solution, namely x1 equals delta, x2 equals 1 over delta. So any slack here is impossible. But this example also teaches us something. These pseudo-solutions will tend to infinity. Okay, so we cannot introduce a slack. What else can we do? Let's, instead of one inequality, try to introduce a family of those and prove some asymptotic statement. And let me first write the expression, which may be a bit technical, but then I'll explain why we do this. Let's consider a function, say f of lambda, and lambda will be a positive real parameter, which is the integral over Rn of the exponential negative lambda 1 over 2 lambda squared summation j from 1 to m a j x x minus alpha j squared times exponential of negative norm x squared over 2 dx. Okay, so let's look at what we have. First of all, if I ignore this part, I have an integrable function. So this is finite for any lambda. Second, this function is always less or equal than 1. And if lambda tends to infinity, lambda tends to 0 here, then this function tends to 0 unless all these equations are satisfied. And then one can consider an asymptotic of this function as lambda tends to 0. Of course, the dominated convergence says that these integrals will converge to 0, but they are going to converge at a different pace. Namely, if there are no solutions, this is going to be converging at the exponential rate to 0. And if there is one, it will converge only at a polynomial rate. Now, how this was written, of course, this is the motivation was probabilistic. This is the expectation of a Gaussian vector. Okay, so at this point, we can say that we have done our job. This is a criterion, and this holds without any assumptions on the right-hand side. It can be any alpha, and without orthogonality assumption as well. So this is the criterion. We can go home. In fact, it's, of course, unsatisfactory. How would you check the asymptotic of this integral in practice? So we have to work more. And before doing that, let me say why this function was chosen. I had a much bigger freedom in choosing a function. What this factor is responsible for is suppressing pseudo-solutions. I know that pseudo-solutions will tend to infinity, and the exponential factor will guarantee that in this case, the rate will be still exponential. And this is just some function which is 1 if the solution exists, and which is less than 1 and quickly tends to 0 if it doesn't. So why these precise forms? The reason is that we know that the Gaussian kernel is a fixed point of a Fourier transform. And we can try to apply Fourier magic to it. Okay. And this indeed holds at this point, though we are going to lose equivalences, and now condition becomes sufficient. This can be, the asymptotic can be analyzed using the Fourier transform. This is not completely straightforward. This exponential is easy to handle. This is a fixed point. But if you look at these polynomials as polynomials of x, this is a quadratic form, and I square it. It's exponential of the 4th degree polynomial. This is not as nice as the exponential of the second degree polynomial. Nevertheless, this can be handled. And we have a condition, so let A1, etc., A, M be symmetric. And by N matrices, and let alpha be the vector of the right-hand sides, and let me introduce another function. I'll talk about it a minute later. Let's say G of T is the determinant of I n minus summation j from 1 to m tja j times times I, the imaginary I, to the power -1/2. At the moment I write this, I owe you an explanation, because this is a complex symmetric matrix. Its determinant is complex. I have to define the square root of it. But that's easy, because the matrix is symmetric, so the determinant is a product of eigenvalues, and eigenvalues have a real part. One, I can define the branch of the logarithm, and just take square roots of the eigenvalues, multiply them, and this is defined. Now, the condition if G hat of alpha over 2 is non-zero, then the system A jx times x equals alpha j has a solution. And again, and this is much simpler than analyzing the asymptotic. I have to check just one number. If it's non-zero, I am done. So again, at this moment, I can go and happily drink coffee, but not really. How to check this? So what is the Fourier coefficient? Let's write it. If I, this G hat of alpha over 2 is the integral over Rn of this exponential, of the determinant to the -1/2 of I n minus I. And let me denote this matrix by A of t for shortness, so minus A of t times exponential of negative I over 2, summation j from 1 to m alpha j tj dt. How do you determine that this is 0 or non-zero? Okay. Let's cheat a bit, and let's first let me rewrite this as the integrand as one big exponential. It's the integral over Rn of the exponential of negative 1/2 log determinant I n minus IA of t minus I over 2, and this sum is actually the inner product of alpha and t dt. And let's imagine that we live in the neighborhood of 0, and we can decompose this logarithm into a Taylor series. So what happens? So again, before I erase it, the main difference between this intermediate theorem and the final version that we aim to is that this condition is quickly and easily checkable. Okay, so what is this? I take the integral over Rn exponential, and then I recall calculus 1 and decompose the log dot into a Taylor series, and it is negative, it's 1/2 summation say k from 1 to infinity of I to the k over k trace a of t to the power k, and then minus I over 2 alpha t dt. And let's look at what is at this exponent. So what is this? Okay, let's look at the first term. And the first term is 1/2 I trace a of t. And also I have another linear term here, minus I over 2 alpha t. Then the second order term is plus 1/2 I squared trace a squared of t plus etc. Okay, so what is what here? Let's see. The linear term, a of t is this matrix, and its trace is the summation Tj trace of a j. I subtract alpha times t. So the pieces of the puzzle start fitting together. We the first change of variables was intended to kill this linear term. So if alpha is a vector of traces, the linear term is 0. Now, what is trace of a of t squared? I open the square as in the middle school algebra class. So this is the sum of over j and l t j t l, and then trace of a j a l. But I already made this system orthonormal, and the reason for that is clear now. These traces are the inner products. And so only the indices j equals l survive. They contribute 1, and this is actually going to be the Euclidean norm of t squared. So when I look at this expression, I have